Hello and welcome back to my channel guys, excelexperthead.com. Today we are going to see motor power calculations for overhead chain conveyor. You can see we have given one picture here which is showing a overhead chain conveyor. This is the track of the chain. These are the hangers which is hanging to the chain at this location, and in the hanger we have some pallet type of arrangement where we can carry our raw material. So you can see we have located a hanger here, chain track and weight to carry. Next we will see the chain track, how the chain track has been designed. Here we have a I-beam which is actually carrying the chain in this track. This is a trolley which is actually connected through the chains. Now you can see we have located a trolley, I-beam, chain, and then we have some hooks hanging below to the chain. In this hook we have to carry a hanger either, or directly we can put some weight to the hanger to carry. So this is a weight. What we are going to learn in this video is how to calculate a total force. In the total force we will see pull force and friction force. With addition of these two we can calculate a total force required. Then we will see how to calculate acceleration of the motor, chain friction, then torque of the motor required, and the sprocket with the PCD, then power required and power required with the service factor. In this video we will able to calculate all these parameters for the motor. Now first point we will see how to calculate total weight to pull by the motor. For this we need a weight of the product. Here we have considered 800 kg is the weight of the product, and we have 18 number of hangers as per the length of the conveyor or customer requirement. These both data has been given by the customer. Now if we multiply 800 kg with the 18 number of hangers, we will get 14,400 of kg product weight we need to carry. Second point we need to see is weight of the hanger. As per our design, we have seen that we have 50 kg each hanger has to be designed to carry the 800 kg of weight. Now 50 kg per hanger into 18 number of hangers equals to 900 kg hanger weight itself need to be carried by the motor. First is product weight, then hanger weight. Now we have some hooks to hang the hangers on the chain. The hook we have designed 5 kg each, and 36 number of hooks we need to install on the chain to hang 18 number of hangers. So 2 hooks for each hanger we need to install on the chain. So 5 kg into 36 equals to 180 kg. Weight of the chain from catalog. So from catalog we will select a chain which itself weighs around 9.67 kg per meter. This is a supplier chain catalog data. We need 110 meter of chain because this data has been given by the customer. He requires 110 meters of chain because the number of stations he has given in his layout. So 6.87 multiplies with 110 meters, so chain itself weighs around 1065 kg. Weight of the chain trolley, because this chain weight is nothing but this chain weight is 9.67 kg per meter. We are not included a trolley required to roll this chain in the I-beam. So this trolley also needs to calculate, because this trolley also need to be get pulled by the motor. So weight of the trolley from supplier catalog. So we need 132 number of trolleys to carry this chain effectively. So 8 kg weight of per trolley into 132 numbers. So it comes to 1056 kg. So total weight addition of all these individual weight of the component is equals to 17,601 kg, which we are calculating around 17,800 kg, which is a load to pull by the motor. Now we will see how to calculate total force to get pulled. Total force F equals to pull force plus friction force, which are denoted here by F1 and F2. To calculate total pull force, we need to first understand this diagram. In this diagram, guys, you can see we have given one object which is connected with the rope, and now we need to pull this object on the steady surface given below. Now to pull this load, we have put some rope tied to the object, and now we are pulling this object with some force. That force is called pull force required to move this object. Now while moving this object, it will create some friction in between two surfaces, because the bottom surface is steady. To overcome this friction, whatever the force required to move this body is called a friction force. Total pull force is calculated with the formula of mass into acceleration. M equals to mass, which is calculated in kg, and A equals to acceleration, which is calculated in meter per second square. Now we have a mass which we have just calculated around 17,800 kg weight we need to move. For acceleration, we have a formula A equals to V minus U upon T. We will see what is these notations says. V means final velocity of the component, which comes to meter per second. U is the initial velocity of the component, if anything, upon T is time, which is starting time of induction motor, which is always given in a catalog. So maximum speed of the conveyor is 8 meter per minute. This you guys needs to be calculated with the help of layouting of the entire overhead chain conveyor, and see how much time you required to move station by station to deliver the customer components, and on that basis we come to the conclusion that we need a speed of conveyor which is 8 meter per minute. So final velocity of the component we can calculate is 0.13 meter per second. This 8 meter per minute we have just converted into a meter per second. Ramp up time, which is we have considered here, is a 3 seconds. So this is actually not a consideration, but it is given in a motor catalog. In the chart, this red line shows how the motor actually behaves. So right now at this stage, t equals to 0 means time equals to 0, because motor RPM is 0. Now when motor RPM goes to 3000 RPM, it requires some time to ramp up, which is called ramp up time of the motor. Again, when it reach to the 3000 RPM and run for certain time, and when you switch off the motor, it ramp down to come to the 0 RPM. So to come down to the 0 RPM, it again requires some deceleration time, which we can call as ramp down time. A equals to V minus U upon T. A is 0.13 meter per second. Initial time of or you can say initial velocity of the motor is 0, and upon time required to ramp up the motor, which is 3 seconds. So acceleration A equals to 0.044 meter per second square required. Now we will put this acceleration into the pull force formula. So here F1, which is pull force, equals to mass into acceleration. Mass we have calculated 17,800 kg and acceleration is 0.044 meter per second square. So answer is 790 Newton, because kg meter per second square is a Newton. So while we convert Newton into the kg, it comes to 80.5 kg. Now we will calculate friction force F2. The formula for friction force is mass into friction. So how to calculate friction? For this, we have a formula mu dash into d, small d, plus 2 into k upon capital D into beta. So we will see notations. Mu dash is nothing but a bearing friction. Small d is a bearing diameter. K is a rolling or sliding friction. D is a roller wheel outer diameter. Beta is a flange friction. So these are the notations. Out of these 5 notations, these 3 which we can get from the bearing catalog. We will see how these all notations are denoted in the diagram. So here we have provided some diagram which is showing a I-beam and the trolley running on the I-beam from both sides, and here a hook is connected to the trolley. So outer diameter of the wheel, which we consider as capital D. Outer diameter of the bearing, which we calculate as a small d. Then flange friction, which is always in between I-beam surface and the roller. Here is a flange friction. Sliding friction consider because some rollers may get jammed in between and cannot roll on the chain, but due to the force of the motor, they get slide on the track. So that's why we need to also consider that sliding friction. Bearing friction, which comes to the catalog. So these are the 5 points we have to consider. So when this roller rotates on the surface, due to the motion to reaction at the axle of the roller comes from the surface contact in between a chain track and roller. So here friction force is get act and then driving force. So driving force direction is this side, but friction is applied to this direction. So here these 5 parameters we have explained. Now we will consider this mu dash bearing friction is 0.02. D is a bearing diameter which is 4 centimeter. A catalog, this both figure came from the catalog. Then K rolling oblique sliding friction, we usually consider 0.05. This is a standard parameter which you can directly consider. D is a roller wheel outer diameter. This is again from the catalog of the rollers, or you can say chain or trolley. Beta is a flange friction, we always consider 1. So both these value you can consider as the standard values. So we will put this value into the formula. So mu equals to 0.015 is the value. So while putting these two values, which is a mass and mu, into this formula, F2, which is the friction force, equals to mass into mu. So now we have calculated a friction force F2 here, which comes to 278.66 kg. By adding these two forces, which is a pull force and friction force, into the total force formula, total pull force is applied on the motor through these pulling action and friction in between the chain, roller and track, it comes to 375 kg. So till time guys, we have seen how to calculate total force, pull force, friction force, acceleration and chain friction, which is mu. Now we will see how to calculate torque. So now calculate a required torque at sprocket. Please remember we are calculating here a torque required to the motor sprocket. So the formula is F into R. F is nothing but a required force and R is radius. So here you can say this is R of the sprocket, radius of the sprocket, and here a force applied on the sprocket. Now calculate sprocket radius. We have considered here number of teeth to the sprocket are 19 numbers. This is just a consideration. We can change that if required. Chain pitch, we have considered 50.8 mm, which is a drive chain. So this value comes from a standard catalog of the chain. So to calculate a PCD, we have a formula P into 1 upon sine 180 upon 9. So P is a pitch of chain, N is a number of teeth. So by putting these two parameters into the formula, we will get a value 308.63, which is a PCD, pitch circle diameter of the sprocket. You can see with this figure where exactly 180 upon N is came from and P by 2 has came from. So we now have calculated a PCD of the sprocket. Now we will go to calculate a torque. So as we know, torque is nothing but F into R. So here we have given a sprocket and here the force coming on the sprocket, and this is a radius of the sprocket. Here applied torque on the sprocket we are calculating. So this figure pretty much explaining what exactly we are calculating here. So force is 375 kg, which is addition of pull force plus friction force. So multiplied by 308 by 63 because we need to take a radius. This is a diameter of the sprocket or PCD of the sprocket. Now we come to the answer, which is 57,750 kg mm. So torque T we required in kg meter. So we divided this figure by 1000 and we come to the figure which is 57.75 kg meter torque required to drive or pull this load. So this way we can calculate a torque of the motor. So after calculating a torque, we require to calculate a sprocket RPM. To calculate a sprocket RPM, we have a formula V is a velocity equals to pi into PCD into N. So why we are requiring to calculate a sprocket RPM? Because this actually requires while selecting a motor from its catalog. So V is a velocity, P is a PCD, which is a pitch circle diameter of the sprocket, N is nothing but a sprocket RPM. So we already know we required 8 meter per minute speed of the conveyor, which is a velocity, equals to pi into 0.308, which is nothing but the conversion of mm to meter of the sprocket diameter, into N. So this way we will find out that we require 8.25 RPM to the sprocket, which is a RPM of motor also. Now we have arrived to the final stage of the calculating required power to drive this conveyor. So P equals to, which is a required power, F into V. F is nothing but a force which we have already calculated. With the help of F equals to F1 friction force plus pull force, F1 plus F2, and V is a velocity which we already know 8 meter per minute. So 375 force into 8 is a velocity divided by 4500. So by this calculation we get 0.66 horsepower motor we required. But wait, we are forgetting some important factor, which is a service factor of the motor, which we have considered here is 0.85, which is 85% efficiency of the motor is considered. So 0.66 is divided by 0.85, which come to the conclusion that 0.77 horsepower motor we required to drive this conveyor. To convert this HP into the kilowatt, we need to multiply this figure with 0.745. So we get 0.57 kilowatt motor we required to drive this entire conveyor. Coming back to where we have started, in this entire chapter we have seen how to calculate a force, then pull force, friction force, acceleration, chain friction, torque, sprocket RPM, power required without service factor, and then power required with service factor of the motor. So this way guys, we can calculate a motor power for the overhead chain conveyor. So please like and subscribe to our channel guys to get such kind of detailed calculations every time. Thank you very much. Take care.